That's the most important thing. Great. So the next item on the agenda is to announce or to introduce the Charles Hatchett Award speaker for this year. This medal is awarded for the science and technology of niobium-based materials. It's an annual award which CBMM sponsor. The official presentation of the award will be given at a separate ceremony at the Institute of Materials, Minerals and Mining. This conference allows the winner to present their work in terms of a lecture. And this year, the award goes to Pete Barnes from Boise University in the USA. This is on the basis of a published piece of work regarding niobium technology. And the paper concerned this year is entitled Electrochemically Induced Amorphous-to-Rocksalt Phase Transformation in Niobium Oxide Electrode for Lithium-ion Batteries. This was published in Nature Materials in 2022. Pete is the first author of the paper. There's a long list of authors who I'm sure Pete will acknowledge during his lecture, but I'll hand over to Pete now to present his award-winning lecture. Okay.
Thanks, everybody. It's a great honor to have received this award. As I kind of, there we go. We talked about it's a really long list of people that helped produce this work, and it was over a period of, Claire, 3 to 4 years that we worked on this project. Countless times going to the beamline, working with scientists, staying up, too many hours to get the results that we see here. And that's kind of why I started with an acknowledgement page right at the beginning to show how important these individuals are. You have a long list of beamline scientists and collaborators, physicists from Boise State, colleagues that I worked with at the university who helped produce this work. As we go through, I think you're going to realize why it required so many people. We stand upon the shoulders of giants, right? And as we go deeper and deeper into these very niche, not niche, but unique phenomenons that, to develop novel materials, it kind of takes that type of effort. And kind of give a little bit of boasting to the lab that I came from at Boise State University. We really focus on this puzzle of creating novel electrodes. Can we introduce defects in that materials? Because that is a very hot topic right now in batteries, and designing that interface in those batteries. And a incorporation of all of that, doing advanced characterization to those techniques, to those aspects of it. And so we look at all the way from being an engineer and engineering nanomaterials to operate in the battery, to doing in situ operando characterizing at beamlines at argon, introducing defects in such as irradiating samples to create defects in the sample to increase the capacity that are held within them, and then or engineering the interface or interphase of a material so that we can increase the capacity of the battery. I just want to say I had a great time at Boise State working with Claire on a lot of those different projects, but this was my bread and butter and main project through my time, or pulling my hair out since I have none left, project. What we, it's kind of a growing field, right, of how we kind of gonna reduce how much carbon footprint we have as an individual. Giving it to the people of how can you do this? Well, there's a large amount of abilities for people to change their ways, but for the scientific field, we can increase how easy it is to get to batteries, right? And we've had this gradually saturated market for the commercial entities, and we have a growing market with stationary energy, grid energy, power at your house from batteries. And we're, as battery chemists, we're kind of walking this tight line of how do we increase our capacity without hindering safety of the batteries, and also without with giving a application-based method to people, right? We want to give them the ability to have high power, right? We want to have them to have high energy and high power, and this is kind of our work to help answer how we could get to a high power anode material. And that tightrope that we're walking, right, is it's a dynamic system in a battery. we have this constant shuffling of lithium, and we're always trying to push, up to this higher, the higher potentials, and the separation, the voltage window that we're operating, separate that as high as we can, with also looking at how the electrolyte is going to interact with those surfaces, and are they going to be stable at those voltages? And so it becomes quite complicated, as we all know. But what we'll be talking about today is an insertion cathode, where we saw has the least amount of volume change associated with it. And also, in addition, the field has really been focused on getting to this defect-driven electrode materials. And we have a case of TiO2, and in the case of showing a amorphous to cubic transformation, we have such things as vacancies put within cathode materials to increase the capacity of them, be it radiation or other methods. In the work today, we're going to kind of go back to Gibbs free energy. I'm not a physicist, but I took thermodynamics a few times because you have to get through school, right? But we know that if we were to look at an amorphous material, it's going to have a really steep slope associated with it as we increase our temperature, right? It's compared to that of other crystalline type materials. And so you can associate that amorphous material as at one of the upper or the higher limits of, you could say maybe a threshold for a metastable inorganic material to exist, right? So if you exist at these black bars, essentially anything that's below them are states which we could get to, but may not be obtainable through normal conventional ways of just heating them. And so if we want to look at selecting the negative electrode for the lithium-ion battery, we have to think about high energy and high power densities, low volume changes associated with them. Is it economically good, a good solution for costs? Do they have high stability and environmental friendly? And our group is really focused on titanium and niobium oxides with a theoretical capacity of 330 and 202, respectively. They have a lot of things that kind of fit in this parameter box that I kind of outlined, but they have the low capacity and they have low electrical conductivity, which kind of hinders their ability to operate in this field very often. So talking about standing on the shoulders of giants, Claire, my PI, she had done a previous work in TiO2 where she had noticed that if she was to cycle at a certain voltage, she would get a phase transformation of the material that would go from amorphous to cubic. And so she demonstrated this by XRD and ZENS to show that the TiO2 nanotubes participated in this phase change. It's kind of an odd approach to start a battery concept with an amorphous structure, right? Blocked pathways happen readily, but the idea is to incorporate amorphous material for a phase transition where you develop long-range ordering but short-range disorder. And so in this case, the lithium being pushed into the TiO2 created its optimal structure, right? It created this lithiated structure that became a cubic structure, which then was metastable enough to stick around after the lithium was removed. So kind of highlighting this a little bit is that you start at this upper threshold, and a lot of times we kind of miss this gap, right? There's this metastable phases that exist that aren't quite approachable through the normal techniques that we normally associate with creating different crystalline structures. And so what's important is that when we put energy, we inject energy into a material, it's both going to have amount of defects energy associated with it, and also it's going to have a stimulated state about it. Those combinations are going to end up at a rearrangement of the materials that is optimal and creates essentially a total energy, which a rearranged energy, which is higher than the stoichiometric, or the stored. What's very interesting about this material also is that you just asked the question about crystallinity and what crystallinity is going to be the best. Well, I have something to say about that is that niobium doesn't know. It has so many combinations. I think that right now, I found 15 at the time, but I think there's a number way beyond that now. I mean, the Germans back in the day had given it names as tief for certain temperatures, and tief for a temperature for forming orthorhombic and pseudohexagonal. And then there's debate about what is pseudohexagonal and what is orthorhombic. So there's a lot that goes into what niobium can do, and I kind of think of it as a Play-Doh, right? You can, its unique ability to adapt makes it very nice to study, right? You have a lot of different things that can happen here. And so kind of going into more, that was kind of a background on niobium and why we had this idea and why we wanted to study it. And now I'm getting into what we actually produced at Boise State University. It first started with that, I showed Claire some pictures of a nanostructured material, and she goes, that don't look really nice to show pictures of. And it ended up creating a lot of differences in height, differences in structures. It wasn't very uniform. And what we found out is that commercial niobiums that we were getting, they're quite rough, right? They have about 44 nanometers in roughness associated with them, even though they're one of the smoothest that we could get. So we developed and pioneered a method of polishing, electropolishing niobium materials down to about 5 angstroms in this 5 micron by 5 micron AFM image. And what that does in a hot glycerol phosphate solution, potassium phosphate solution, we see that now you get from these not really nice structures to this very uniform anodized polish, or this anodized niobium metal, niobium oxide. This, I was surprised that this has actually reached way beyond the field of batteries now, supercolliders and stuff like that. There's papers out there that have this method as being one of the ways that they want to do it, which we accomplished with a low temperature sulfuric acid and methanol electropolishing. And so if we take a little bit off of the top, we can see that very uniform structures throughout the niobium oxide. They end up creating this amorphous, what we called NCNO, or amorphous nanochanneled NB205. Now, kind of a cool thing that's happening here that you can see on the screen is that there's a video playing that's showing the voltage profile and also a DQ/dV, kind of similar to a CV, right? A lot of you might be surprised because it's changing rapidly over time. Each cycle we're seeing it, the profile of the duct shape is changing. It actually goes from something that looks quite irreversible to something is really reversible. And so this voltage profile is characterized by that, where I want to say is if you pay attention to below 1 volt, at the first cycle, you're going to see that there's a large hump associated with that region. And what's happening here is that this large hysteresis that you see is associated with the phase change that's happening at that low end, or while we're inserting lithium into the niobium oxide, and observing this amorphous to cubic phase transformation below the 1.1 volts. So at our pristine material, we have purely amorphous niobium oxide. On the first cycle, we start to see that there's these nanocrystalline rock salt niobium oxides forming within the material. And upon the 20th cycle, we were no longer able to see any amorphous material available. And it was confirmed by doing SAED, where we could see regions, not just the surface, but regions across the tubes, or the pores, were crystalline in nature and matched that of the rock salt structure, along with observing an XRD. and seeing the radial distances are associated with that discharge to that rock salt structure. Another important prospect of this is that we don't have a constant phase transformation that's destroying the materials. So you can see from after we've cycled it, if you are at a charge 0.9 volts, you still retain the rock salt all the way up to 3 volts. You retain that rock salt structure, so after delithiation. The Gracing incident synchrotron also helped us confirm by giving that kind of angle that we had the rock salt structure throughout the material, and that the ex situ XFs indicated an AC transformation by the NBO and NB-NB bond lengths. So we now have this idea of this lithiated rock salt structure, and how it was developed from cycling. So using electrochemical method to develop a new crystalline structure. And now we want to test, okay, why are we, at this point, we're like, wow, we're getting a lot of capacity out of the niobium oxides. There's really why should we should only be getting theoretically 202. I went to Claire and I was like, I'm getting over theoretical capacity. So Claire was skeptical, I would say. So we had to do a lot of work to see, was this really what was happening? And we were able to use Zenz to see that the niobium oxidation state when we were doing a full discharge was a lot closer to where we had 3 lithiums that were inserting into NB205 rather than just 2. And so that's why we were getting such high capacities compared to what theoretical would have shown. And DFT simulations actually proved that this is pretty accurate. So you're seeing here the voltage profile in conjunction with a DFT simulation on where we would see lithium in this NB205 structure. We were coming out pretty dang close in capacities for that full lithiation. Now, if I don't go below 1 volt, we don't see this phenomenon take place. So if we keep the voltage above 1 volt, we stay at this amorphous state, right? It requires the reduce to go to that low of voltage in order for it to develop the rock salt structure. And we started to do comparisons then. So if we keep the material amorphous, or if we keep it as a rock salt, what happens to the response of the material? Well, as a rock salt, we saw that electrical conductivity dropped significantly, and lithium-ion diffusivity increased dramatically. So orders of magnitude larger in electrical conductivity, and then a doubling in the rate at which it was able to accommodate for the amorphous type material. So again, this is just a repeat of the last slide, but we wanted to see this visually, and so we used peak force tuna to give us, so what do we see on the amorphous structure? Well, at these same sensitivities, we pretty much have no signal associated with these amorphous niobium oxides that have been cycled the same amount of time as the rock salt ones. But when we put in the rock salt one, we see these pathways throughout the material where you have a greater transfer of electrons through the material at those sites. The peak force tuna essentially is seeing how those electrons are going through that oxide material. So we have this rise in the lithium diffusivity, which was also demonstrated by GITT. And so in GITT, we're seeing that we have a faster rates of diffusion associated here, orders of magnitude, almost order of magnitude larger. And then you have an improved current response between the rock salt and the amorphous, especially when it comes to the low voltages associated with them. Now, how do they perform as a battery? That is a really important part. Now, with that high electrical conductivity, which we talked about as being a poor for niobium oxides before, if we improve that and we improve lithium diffusivity, this should help the rate capabilities of the materials. And you can see here, the rock salt material is really stable, right? I'm going to actually jump over here. It's really, really stable. Over 400 cycles, we saw I can't remember the exact number. I think it was 99.3 or 99.93. It's quite great. But on the rate capability size, we see that once we get to about 200 milliamp per gram, we're seeing a dramatic increase in the amount of capacity that can be contained in the rock salt structure rather than the amorphous structure. So there's obviously less impedance that is happening in the cell while it's happening at fast rates. And you can kind of tell this also by looking at the current densities as they go over the voltage, how different they are in comparison to amorphous to rock salt, right? This has that kind of characteristic, capacity type response where the rock salt has that of the normal battery that we would like to witness. And I think I'm kind of getting out of time, but why this happens in fast, why we're seeing this fast lithium diffusivity, it was studied by Professor Shuping Ong, where you have this octahedral to octahedral jumping for the lithium. So it's creating these little highways for the lithium to transport through the materials, where it's getting blocked in an amorphous type material. And to kind of summate this is that, we need to think more about just adding heat to a material to create structures that we want. We want to think about electrochemistry as can get us to these metastable states that have better properties for batteries. And so, for example, Claire's work showed in the TiO2 nanotubes where they had the amorphous to cubic structures. And then we have all the work that I discussed here today showing that the niobium oxide can also go through that same phase transformation. And then such things as the manganese oxide, the halidite and the pteridotite they happen in nature at low temperatures, and we have a hard time creating them in the lab. And that's because plants and other plants are able to utilize electrochemistry way better than we can, right? They're able to do enzymes and all sorts of chemistries that we don't, even though this is probably one of the most common structures in nature. And to kind of summarize that is that we really want to look at this defect-driven nanostructured metal oxides for energy storage. And it can be such things as coatings, it can be full-on applications of these materials, but it really highlights now and you can even look at there's another work on vanadium oxide that came out. So we have work in titanium, vanadium, and niobium. And this is unpublished results, but we have also seen this same phase transformation takes place in tantalum, but the capacity of it is a little bit low, and we're trying to figure out why that is at this point in time. So with that, I'd like to thank your attention, and I hope I didn't go too long. I just highlight all the people that I worked with. There's a lot more too, but these were the groups throughout the year I was at EEML. And with that, I'll take any questions.
Great. I'll have to shout. So thank you very much, Pete. That's really great. It was a very clear presentation. You didn't overrun, don't worry.
Okay.
We have time for some questions for Pete, if anyone has one. Ron, you were fast.
Yeah, my question is regarding the rock salt structure, if we can have it only electrochemically induced, because at the lab in our factory in Brazil, we never seen rock salt structure when you start on amorphous phase.
Yeah.
It's increasing the temperature. That will be the question to me.
So I would go back and look at this chart of here.
Yeah.
Yeah.
That's the typical phase transformation that you see in the lab.
Yeah.
That's all the time, yeah.
So what I would say to that is yes. Right now, that's the only evidence that we have for forming the rock salt is through electrochemistry. Does it have to be lithium insertion? I don't know. I think that's a question that can be answered more. I think that there are more than just lithiation that can cause unique crystalline structures to form. In this case, rock salt might be the only one that this can be done with lithium, right? As we push that lithium in, we're causing the niobium to, it develops what I believe is a gradient in the materials, which then eventually the niobium's like, I don't like this structure. I'm gonna tweak a little bit to allow the lithium to come in, and then it's metastable enough that it's not gonna revert back to the amorphous. So that's why it has to be below that line that I showed.
And the other question is very quick about the electronic conductivity of the rock salt phase. Have you measured the electronic conductivity?
Yeah.
Yeah, just maybe I'm missing the presentation.
No, that's fine. Yeah, so electrical conductivity, we did 2-point probe measurements, essentially looking at the pristine. We get a rise when we have the amorphosis, probably stuck lithium in the amorphous structure, and then a 2-fold increase from there. Puts it in the semiconductor range.
That's what I would expect. That's great. Thank you.
Thank you. Any more questions? Mark.
Oh, yeah, sorry. That's fine. Thanks. Thanks for the talk. I really liked and appreciated the Play-Doh analogy. It was pretty fun.
Yeah.
Okay, so this is the perfect slide that I want to ask a question on. So I see this beautiful forest of a microstructured material, let's say 10 microns tall. Maybe it's even higher than that.
10 microns, yeah, you got it right on.
When you put on your cell manufacturer hat, how do you exploit the power of these rock salt structures if you're going to actually build a cell? Because this is a flat forest, right? And you're actually going to make a slurry and make an anode or a cathode or whatever. How does that work?
Well, that's kind of a creative type process, right? But you could think about, I could say even that these could be layered within materials. But also, I have the question of, as the field of niobium goes into these adding the niobium oxide, maybe they need to start with a dopant that's amorphous at a nanostructure, because that's not the only nanostructure that can do it, right? So I think that's more of an engineering thing. I think that the principle here that it happens is clear, and it happens with a lot of transition metals, and that we're not able to get them unless we do it through a different method. Yeah. Does that kind of answer your question?
Yeah,
kind of skirts it a little bit.
It kind of, and I do the same thing. It's an engineer's problem, not a scientist's.
Yeah. I mean, I love answering the engineering problems too. Claire knows I don't like the word tinkering, but I like to play with a lot of things, right? So, like, to be honest, this was an accident. So, real science sometimes happens from accidents that we learn how to what happened here. At first, I was supposed to cycle to 1 volt. I was in organic synthesis at a pharmaceutical company before I was material scientist, and I had just read a bunch of other niobium papers, and they had gone to these lower voltages, and so I went to 0.5. And I saw the hump, but you don't see the hump when you're above it. So if I hadn't have made the mistake of putting a cell out at a lower voltage, I would have never seen this, right?
Another question here.
Thank you very much for the talk. It was really inspiring. You showed a very beautiful, colorful image where the lithium was going in and out, right? That was the area where lithium was going in. It was in goldish, right? Could be. Yeah, no. Okay, sorry about that.
It's okay.
Anyhow, yes, voila, there you go.
Yeah.
So in this part, you're showing that the lithium actually goes only in certain parts of the surface, correct? At the same time.
What you're seeing here is atomic force microscopy using peak force tuna. So you're seeing tunneling, electrons tunneling through the oxide.
Okay.
So if we're to go back and look at it right here, you're seeing the AFM is coming from the top, and you're having a current supplied at the bottom. And as the tip of the AFM comes closer, those electrons can, depending on the current that's being pushed through and how it'll feel how much is able to come through with the voltage applied across it. And so in the comparison here, the AFM tip pretty much saw nothing at those currents, right? So we had to go through these iterations of voltages we were putting on the other side of the material. And this is in a glove box AFM. And then when you put with the rock salt one, when that tip gets close enough, that electron is going to shoot through those.
Exactly, but so you showed also this forest, right? So how does the forest match this picture there? So
Yeah.
AFM, I actually used it, so thank you for explaining.
It's not, so AFM you normally think of as giving you topography. But peak force tunneling is electrons coming through. So if you could go, let's go back to here. So as it went across, that tip isn't really sensitive enough to get down to these 20, 30 nanometer size holes, right? The electrons are going to jump from these walls. And it's just not sensitive enough to show that, to show that detail of electrons coming through. Does that make sense?
Yeah, it makes a lot of sense.
Yeah.
So that's why. Okay, now I can reconcile it.
But this is more macro electric current coming through.
Yeah.
Yeah.
Thank you so much.
Yeah.
Okay, we've got one more question.
Thank you. I'm Sukhdev from Niobium. Interesting results.
Thank you.
So I have a question in terms of the properties. Did you observe in variable properties in the directionality in terms of course, there's a symmetric structure considering the rock salt structure, but do you observe any change in electronic conductivity or the lithium mobility, which is directional in terms of the structure?
So, for us, I would say to look at I wish I could pause this. Let's see. So, you're saying, did we see any difference between these peaks and which way we're charging and discharging?
In structure, I mean, in case of the block phases, you see they're actually unidirectional in terms of how the lithium can get in, and also the conductivity is actually different in terms of the lateral and
From the 110 versus 111. Rock salt's a hard structure to get that kind of detail on, as you can see from our XRD, right? There probably is. I mean, we're nanostructured, right? So we're seeing these nanocrystalline materials within the SA that we're seeing in the high resolution TEM, right? So I'd venture to say that probably yes, but I don't know for sure.
The reason behind my question is that I think you've managed to kind of grow these as tubules, and probably you know the direction of the way in which these electrodes are constructed. So I thought it would be an interesting thing to actually easily visualize, because in general it's hard to measure these things on this market.
And I would say that it's not a perfect rock salt too, right? Because we're going to have defects inherent in this type of growth, right? That's kind of why we talk about it near the beginning, is that it can't exist as this nice crystalline, really defined crystalline structure. So I would say that one of the benefits of this is that when you're lithiating it, the lithium is going to occupy sites and change niobium to the lowest energy. And so whatever that surface is that the electrolyte is in contact with is probably going to rearrange itself such that it's the highest conductivity, right? I don't know which direction that would be, but I think that the electrochemistry is pushing it to be the lowest barrier for the lithium to be inserted. Yeah.
Okay, well, thank you everyone for the lively discussion and all the questions. We need to stick to schedule as we've got a lunch break before a busy afternoon session as well. But perhaps we should thank Pete for a really excellent lecture, and congratulations on winning the prize.